grab a recording of the rest of this so that they can get caught up. So for a quick recap, what we've got here is we've got our step one. We aren't doing any introduction of variables. Step two, we start our serial read. Step three, we're actually setting up the initial read of the analog data. Then we're using this function that we found on the Arduino language reference called map. So this is one that allows us to change one set of data, for instance, a scale from 0 to 1023 to our new scale, which is -40 to 125. So what that will allow us to do is that will allow us to see what the new range is for our sensor value. The reason we have to overwrite this is we either have to overwrite this and store the new data from sensor value that's coming in up here into this map function, or we have to assign a new variable and call it sensor value 2 or 3 or whatever. But that can get pretty confusing pretty quickly. So it's helpful to reassign this if we know we're only ever going to use the actual temperature data, so that as we change the temperature, we see that it's actually very accurate. So this behaves linearly, where an actual sensor, an actual temperature sensor is a little less linear than the behavior of this one. So this code would work fairly reasonably for the same part number of temp sensor, but it's not going to work for one that you build with a voltage divider. So we'll look at an example of that as well. So there's a couple other things that we'll do. There's a couple issues with connections back and forth. So there's internet that's been going in and out on the dorms and all kinds of other places on campus. So yeah, there's all kinds of really, really cool stuff that we can do with these. And the map function really saves us a lot of headache for a lot of simple examples. So what I'm going to do next is I'm going to comment this out, and we're going to take a look at building the equivalent of a light sensor. And so instead of a temp sensor, what we're going to do, this is where I'm going to have you guys work a little bit to see what you can determine. So it's still going to be power, ground, and signal. I'm going to move stuff around slightly. And I think this is about enough room. Let's see. See if I remember and get it right. What we're going to do is we're going to take another common sensor, the photoresistor, and a resistor, and we're going to build an equivalent of a photosensor. I'm going to see if you guys are able to make that work. And I may or may not have done this enough times that I remembered exactly what the spacing has to be to get it right. So what we have here is the same kind of 3-pin sensor arrangement as a temp sensor, or for instance, as a, I think it's under the all components. So there's some additional input types, an IR sensor. So this is another type of light sensor, power, ground, and signal. So you'll see this over and over and over again in 3-pin sensors, this power, ground, signal type of arrangement. So what we've done here is taken a photoresistor and we've built the equivalent of a photosensor. So we have power on one side, we have our signal. This is using a principle called voltage division. It's not important really to understand exactly what that is at this moment. This is just a mechanism that we use to build circuits. So what I want you guys to do is I want you guys to see if you can use something like the map function to get useful data out of this. Because what you're going to find is this has a range of brightness, but it's going to behave a little bit differently. So I'm going to set you guys up in the breakout rooms, I'm going to have you guys in class also do the same thing. I'm going to see if you can figure out what to do with this signal and whether or not it's analog or digital. Go ahead and resume recording for this as we're talking about a couple of the functions. So instead of just being able to do some math steps, things like squaring and square rooting, if you were to take code like this and you were to say, for whatever reason, I wanted to take the sensor value and I wanted to square that. In math speak and in notation, things that we'll use later on like MATLAB, you can use the caret and a 2. The problem is if you try and do that here, we end up with problem. So it goes, yeah, I don't really understand what happened there. So we can't do a square of the sensor value. One thing you can do is you can use this function, talking about math operations, SQ. So this will square, meaning multiply a number by itself. So this is a function that saves you a small amount of typing every time. So square of this sensor value, that will square the sensor value and get rid of our error. This one might actually have to, include the math library, because this one may not be included, at least here in Tinkercad. It may not be included in the default library. But square is one method. The other method is to multiply it by itself. So you can do sensor value times sensor value. But another reason that this can have a problem is sometimes you'll have to move something to a second line in order to not be reassigning a variable, for instance, inside another function. You can create extra headaches for yourself that are unnecessary. So if this doesn't work, you could say, you could redefine sensor value as the square of sensor value. So if it's included in the default library, that should cooperate. Yeah, so that will. So same problem with our sensitivity, just exaggerated because we're squaring it. Or you can reassign it by saying sensor value times sensor value. So that doesn't save you tons and tons of typing, that square function, but it is one that's included in without including the math library. So that's helpful for you guys to know for later. So this will give us the same range of data. Go. So give us the same range of data, the same effect. It's just a slightly less typing overall to use the square function. So there's some other math functions, but to get too far into those, we start getting into libraries and things that we'll get into much more detail a little bit later. So one of the things I want you guys to try next is under some of the ones that are included here, some of the other functions, I want you guys to try and run some of the functions, things like maybe the cosine, sine, tangent, the absolute function, some of these others. I want you guys to try that on this data. The notation you're going to need to use is going to be like this, where you're assigning a calculated value back to the variable. Because if you try and do math on the first part of that, you're going to come up with all kinds of errors, and that's what you're seeing in this process. So you have to be very intentional to assign the calculation on the right side and your variable that you're storing it to on the left side. So I want you guys to take a few minutes. I'll reopen the breakout rooms, and that will give us one more thing that we want to work on. The last few will join us here again in another few seconds. There we go. We should have everyone back now. So one of the last things that I wanted to highlight for today is the fact that you can nest some of the functions. So you guys will see an example here where you can take an operation and then do something and then undo it, do something and undo it again. So for instance, taking the square of that sensor value, then taking the square root of that squared sensor value, taking the square of the square root of the square of the sensor value, and then of course obviously taking the square root of the square of the square root of the square of that sensor value. So what that can do is do and undo operations. You can also nest some of the other functions, and you still get the same range. It just may slow down the calculation a little bit. So depending on what you're doing, you can have lots and lots of different kinds of functions, and you can nest them. So you can do one kind of operation, then another, all at the same time. You just have to be very careful about doing that. So it's clean and efficient to do stuff like that all on a single line. But the idea is you always want to be focusing on trying as much as possible to isolate them and sort of do them one line at a time. Why do you guys think that might be? Any ideas? Why would we want to do those one at a time instead of grouping them like that as we're just learning?
If you did one at a time, it could be easier to find an error, while if you put them all together, then you have to go through each individual part to find the error.
Exactly. If you're coding and you're trying to make stuff overly complicated, kind of unnecessarily so, what you can end up with is you can end up with there's some kind of a problem at line 19. Well, okay, if line 19 is trying to do 12 things at once, that's something that can be very, very hard to diagnose later. So we're going to get into some examples where this is used a lot more heavily, but this is one of the main differences as far as how some of these operations are handled. So there's a bunch of different stuff that we have to pay attention to as we go to build more and more and more complex programs. But this will suffice to give you guys kind of a little introduction for using functions and how functions can kind of be nested together to do things. And especially as you guys are spending a lot of time learning some of this, you want to spend a lot of time looking at the language reference to get a sense of what it is that you're actually doing, because this all makes a whole lot of sense right now. As soon as we go to start applying this to the actual Arduino boards, the difficulty is going to ramp up pretty quickly. So I hope everyone has been following along carefully. So we're going to do our wrap up and clean up here. Are there any questions that you guys have?